Time, remember we talked about, you're getting into eddy current testing, we looked, ultrasound testing, and we looked at wave properties. That's where we started. So we looked at a transverse wave versus a longitudinal wave. Who remembers what they are? Who can describe let's start with a transverse wave. Blanca.
So I believe a transverse wave, like going on the slinky model, was when you like kind of shook it and it went side to side.
Wiggle it side to side. It's like a dog wagging its tail,
yeah.
Right? That's transverse wave. So that's a pulse going out and back that you can see traveling through. So which one, for most of what you're going to be doing is pulse echo testing, which one do we use then? We're going to use a longitudinal wave. It's that pulse. It's that wave, what they call a wave front moving back and forward. And we saw that when we sent that pulse down the slinky, it went all the way to the end and all the way back, and we could time it, right? Or when we put some kind of a obstruction halfway, it would go halfway and back and would come back sooner. It would be faster, right? That time would be shorter. And so we can use that to figure out how deep and how large where damage is in a part. And then we went on to talk about how fast the sound travels and what affects the speed of sound in a material. The what? The density, right? And density changes with what? Temperature is a big one. Pressure on gases, but we're mainly looking at looking at solids in this case. Okay, so temperature can affect that, and it's not always positive or negative, right? Water does a really weird thing where it gets less dense as it turns into a solid. Most materials get more dense as they become solid, but certain crystalline structures can change that. What about when we're setting up our machine? Or we're doing settings, can we affect that speed of sound in a material? No. So the speed of sound is fixed, other than temperature and environmental type things. Okay. So getting into today, we're going to talk a little bit more about sound and some of the properties of that, and then we'll start looking at the actual testing equipment itself. So some things to know. First off, acoustic impedance. When we did the slinky, did you notice when I first put the pulse or the wave in, right, there was a certain amplitude, right? Amplitude, how far I swung it side to side if we were doing a transverse wave, or how big of a kind of a gathering there was. What happened to that as it traveled down and then came back? Especially when I did transverse side to side. You see any difference in that wave when it went down and got back, like how far it was moving? So when the resistance from that wave traveling through the slinky, or sound traveling through the air, as it goes along, there's resistance it has to overcome. And that resistance is going to reduce the amplitude, and that's what's called acoustic impedance. This is the property where if I stand close, I sound a lot louder than if I'm far away, right? Airplanes taking off out here, if they were pulling power right outside our window, we wouldn't be able to hear what's going on, but the planes taking off on the runway are much further away, and they don't cause, we can't even hear them with the sound deadening that they put in the new building. So that is acoustic impedance. The resistance to the propagation is going to cause the amplitude to decrease, okay? Acoustic interface, this is the boundary between any two materials or areas of different acoustic impedance. So you're going to have a probe. Here, I got a big probe here. I've got a probe. This is the face that sound comes out of. When I set it on a material, right, the face of the probe and my hand are two different materials, right? So you're going to have a plane or a place of acoustic interference right there. Where it's first on a material, when it's sitting on a material, that's called the front wall, okay? Now, on the other side of my hand, it goes from, or inside my hand, right, it's going to hit bones, it's going to hit tissue, it's going to hit all that kind of stuff. Or inside of like a composite, you'll have fiberglass strands, and then the plastic resin material. Every time that material changes, that boundary layer of different acoustic impedance, you're going to get an interface, which is going to cause some kind of an echo. So you can see where like a composite, that's a lot of different materials all sandwiched together, you can get a lot of these echoes going back and forth. In fact, this big transducer I have in my hand is designed for doing composite inspections versus where you have a lot of that interference and a lot of that. Versus when we're doing aluminum parts, the transducer you're going to use is going to be about this size. Because there's a solid chunk of aluminum pretty much it doesn't have all those different, all those different interfaces. It's homogeneous versus composites that are not homogeneous. Acoustic attenuation, so that impedance that resists it, the attenuation is the actual loss of energy or the reduction in amplitude as the energy goes through the material. The back wall, so I mentioned with this on my hand, I have my front wall echo. The back of the part is called the back wall echo. Okay, when we had the slinky, the back wall was down at the far end when Colin was holding on to the slinky. Okay, that was our back wall, and then the echo coming back off of that was the back wall echo. And then finally, we're going to have background noise. So nothing in the environment, for our environment, you don't have to worry about, it doesn't have to be like a super quiet room. Okay, if you're doing ultrasound, people can talk, people can be moving around. What you do have to be aware of is if you're working on equipment that's energized, things like motors, things that are running, things that have, so there may be some high frequency vibrations coming out of like a motor that's spinning really fast, right? A motor that's spinning at thousands of RPM, it's going to have a several thousand hertz frequency coming off of it. Okay, you hear that sound. And so just understand that kind of stuff, vibrations that travel through your tabletop or other stuff, can potentially have an impact or can show up as a received signal. It's a microphone. Microphone doesn't care. Now there are filters in there. The testers are designed to help filter that out, but you can still get an effect if you're testing in the 100 kilohertz range, and there's 100,000 hertz sound traveling through a piece of material. You wouldn't be able to hear it. It's outside of the range of hearing, but that little microphone, the little piezoelectric sensor inside of here would be able to hear it. The echo reflection of the sound, it's typically from an acoustic interface, the back wall, or a flaw. Okay, you're going to get it from everything like that. A flaw is a type of acoustic interface. A back wall is an acoustic interface, right? Where the metal or the part is sitting on a table, you've got an acoustic interface there. Okay. The gain is the amplitude, is the amount of signal power measured in decibels. So we're listening for that echo to come back, and we're going to run it through an amplifier. An amplifier is, the gain on the amplifier is how much we're going to boost that signal before we send it to the display. Okay, we're going to convert it into a picture, a display. You're used to gain on, like I said, like a microphone. If you turn the gain up too high on a microphone, it gets really distorted. Same thing can happen here. But if you have it turned down really low, if you're not listening very closely, you'll miss smaller items. So it's a balancing act of turning that gain up to be able to hear really small things, but at the same time not overwhelming yourself, right? When we have our probes, what's going to be happening is these are going to send out a pulse. Again, if it's 100,000, if it's 100 kilohertz, 100,000 hertz, it's going to send out 100,000 pulses per second. Okay? And so the initial pulse is those echoes, those pulses, as soon as they hit the acoustic interface, as soon as they hit the face of this sensor and the material it's on, you're going to get a big echo right there. And so you get what's called the initial pulse. And that's a signal that'll be on your display that it's a non-relevant signal, right? You can't do anything about it. It's part of the feature of this. But what we got to be careful of is the higher your gain is set, the bigger that initial pulse will be, and the more it'll obscure indications that might be near the face of the sensor. And so we have to make sure it's, again, balancing. How far do we want to penetrate the material? What kind of do we want to see? Versus how much is it going to interfere with our ability to see smaller things closer to the sensor. The last one here is piezoelectric effect, and so that ties into how our sensors work. Anyone remember how piezoelectric works? We talked about this in systems class. Yeah. So a piezoelectric effect is we have a semiconductor crystal that when a AC current is run through it, it will vibrate. It turns that electrical energy into a physical motion, energy of motion, kinetic energy, a kinetic motion energy. And you attach that to like a membrane or a film, and as it vibrates, that's going to send out a sound wave. Okay. The reverse of that is when if you have a piezoelectric crystal mounted to like a membrane, typically it's a metal membrane, it's a little very thin piece of metal. When sound hits that, or any vibration for that matter, you could physically tap on it, would do it too. That crystal is vibrated and it sends back a signal. Okay? And so the probes we have, almost all the probes we have, use a single piezoelectric crystal. Okay? And we send pulses to them, 100,000 times a second. That crystal moves, basically vibrates 100,000 times a second. At the same time, when those pulses hit something and come back, they're gonna basically bounce against that same membrane, same crystal. And it's gonna send electrical pulses back the other direction. That's one way to do it. The other way is, on some testers, rather than doing pulse echo, is we can take two probes, and usually they'd be identical, like the probe in my left hand, we have these in pairs, but I'll use this one because it's kind of similar. And so for this one, what we can do is put them on two sides of an object and send a pulse from one and receive it the other. So one acts as a transmitter, the other one acts as a receiver, a microphone. One acts as a speaker, one acts as a microphone. Okay. Our through transmission probes, the one in my hand here, they're kind of medium sized. No, where are we? Actually, I didn't bring one with me. I didn't bring the through transmission probes. We've got two pairs of them, two sets of them. And so you hold them across from each other and you look for the sound to make its way through. So you're not looking for an echo in that case, you're looking for the direct transmission of sound. So that brings us to this method, pulse echo, is what we're going to be doing most of the time. So that's what, in fact, all the probes I have here are, besides the angle probe, these are all forms of pulse echo probes. So we're going to send out a pulse, we're going to let it hit something, whether it's the back wall or some other acoustic interface, which could be a flaw, and then we're going to pick that back up when it comes back. The range on our display, when we're working with our display, we're going to have to set how far of a distance do we want to see. Do we want to see 1 inch? Do we want to see a half an inch? Do we want to see 6 inches, 12 inches? This ultrasound can do fairly thick materials. It can do materials that are several feet, or when you start doing like, remember we talked about surface wave or shear wave type setups? You can do like pipelines that run underground. They have one little exposed area, and they can do a test that goes a mile down a pipeline and back, where it runs through the ground to look for cracks in like a pipe. So that's pulse echo. Through transmission I talked about, we take a pair of probes, send it from one end to the other. But, sorry, I got ahead. Range, we got to set how far on our screen we want to see. The velocity, speed of sound through the test piece. And then this last one is what's called zero offset, and that is in all of these probes, everything I got here, the piezoelectric, the thing you see here, these two, it's kind of this pinky color, pink purple color. That's not the transceiver, that's not the transmitter receiver, that's a wear plate. So the crystal is actually behind that. So the crystal is there, it's going to send a pulse, it goes through this wear plate, or this probe here I have is what's called a delay line transmitter. There we go. And this one is, if you're trying to find surface defects, there's the actual piezoelectric crystal. And then it's got this piece of acoustic rubber on the end of it. And it sets the piezoelectric crystal away from the surface so that you can actually see stuff closer to the surface. So your initial pulse doesn't affect the ability to see things near the surface. So these are good for finding stuff closer to the surface. But what we have to do is we say, okay, this probe, if we couldn't offset the 0, the signal we would get would say, well, 0 is down here, where down at the base of this thing. We've got to offset it, move it to say, actually, the 0 is up here at the very end of this delay block. So again, quick reminder, the frequency range, we're going to be 100 kilohertz, 100,000 hertz to 25 megahertz. And we've done these. So piezoelectric element, converting mechanical to electrical and electrical to a mechanical. I basically did the TED video there, but if you want a little more explanation, you've got that. The key with these is the mechanical vibration and the electrical, the AC voltage running through it are going to be the same frequency, because it's the actual AC, changing polarity that causes the crystal to vibrate. And same thing, when the crystal picks up a vibration, the electric signal it's going to generate is going to have the same waveform, the same frequency, same amplitude changes as the one. These are often made of quartz, lithium sulfate, or barium titanate. Going off memory, but this big sucker right here, I believe, is a barium titanate. And I think most of ours are. That's going to be the most expensive. Some of them might be lithium sulfate. That's a little more sensitive. So inside, this is what I was talking about. So if I have one of these probes, you can see we've got our wires coming in. There's a backing material here, an epoxy potting. We want our sound, we want our ultrasound coming out of these probes to only go one direction. Right there, this probe right here, it's designed to come out this face right here. We don't want it going up into the air. Same thing with this. We don't want it going up in the air. We want all our sound going down into our part. So this upper part, this thing's kind of heavy when you pass it around. When you feel that, the weight of it is the potting compound. It's a very dense material. Up here, potting compound and backing material are very dense materials that are designed to essentially reflect all the energy down. Okay, we don't want the energy going up. So we've got our cable hooked up to it. There's our piezoelectric crystal with the electrodes coming into it. And then the wear plate on the front, which is the pinky purple part there. And you pass around, this is the delay line transducer. You can see that clear plastic part is basically the wear plate, an extended wear plate. When we use these, we have to couple. We want to try to make that, especially that front, right? We want to be able to see into the part. We want to reduce the effect of that acoustic interface at the front wall as much as possible. And the way we do that is by acoustically bonding the transceiver to the workpiece. And we do that using a coupling gel. It's a glycerin-based gel. It's kind of a slippery. I tell students this because it is what it is. It's very, very similar to KY jelly or products of that nature, okay? It's fairly non-toxic. Again, glycerol-based, it's a main ingredient in hand lotions and stuff like that too. But you don't want to get it all over you. I mean, it's got some other chemicals in it and stuff. But what that does is it fills any, this shows a fairly flat workpiece, but when you look at it, there's a grain to the metal, right? And that's going to cause a little, at the microscope, we get real close to it, it's not going to be perfectly flat. It's going to have ridges and valleys and all that. And the face of the transducer, even though it's a flat wear piece, it also is not going to be perfectly flat. Here's the little one. You'll use these probably more than any. So between the face of the transducer and the workpiece, we'll put this, and that's going to fill in and bond. It's going to fill in all those little gaps, all those little air gaps and everything else, and then bond it to it. And that's going to help transfer the sound into and out of the material as best as possible, or as smoothly as possible. Okay. We got to keep in mind the fact that sound doesn't just travel straight out. Okay, these are focused. The sound is designed to come out in a cone pattern. And what we got to be aware of is the waves kind of they point in towards each other, so they're going to come together at what's called a focal point, and then they're going to spread once you get past the focal point. And that divides this into what's called the near field and the far field. Okay? The near field waves, when they're in that area, these sound waves are bounce into one another, especially the waves that are leaving as well as the waves that are coming back from the transducer. And so what it causes is you get a lot of interference. So that's why, if this is our crystal, and we would have a little bit of a wear plate in front of it, there would be, if I draw the wear plate in, there would be a wear plate right in this area. That's going to block us from being able to detect anything in that near field area. So this is why ultrasonic testing is not really good for surface damage. It's primarily designed for subsurface, finding subsurface flaws. Okay? That's in contrast to in the far field area, because the sound waves are starting to spread out, that you don't get those waves bouncing into each other. You don't get the interference. Okay? So I've got a video that shows kind of how these areas work. So what the near field looks like when the waves are hitting each other. So what that results in is we have a dead zone. And it's combined, the first part of it is that the echo, any kind of echo that we get, or there is going to be an echo off of that front face of a part, and goes right back into the transducer. That's going to interfere in that area, and that creates that initial pulse indication. So any return from a flaw on the surface or in the near field area is going to be basically impossible to see. Again, the delay line transducer, that's the whole point of this, is we take that near field, we move it into this clear plastic part, or this clear acoustic material, so that the near field is, so that you're in the far field region by the time the sound gets into the part. So something like this is designed to find flaws closer to the surface, because we've moved the transducer physically away from the part, but we have to offset our time signal to make up for that. Another way to look at it is like this. So if you see the beam, you can see that near field there, and then those are an illustration of the pressure waves in the far field, and how they're kind of, as they separate out and spread, they're not going to interfere with each other. Okay. Or you can look at it like this, and this is the angle that we're going to be testing most of the time. So we've got our transducer at the top, and it's showing what's called the angle of divergence. So the sound is focused together. It's designed to come together at that where the transition from near field to far field is, but then it's going to continue to spread out at that same angle. And so we get gamma, the angle of divergence. Now, where that becomes important is just understand that we are going to see, if you are looking for a flaw down here versus a flaw up here, okay, that are the same size, which one is going to have a bigger return? For two reasons. The one at the top, right? Even though those flaws are about the same size, the top one's going to be reflecting all that energy. Okay, that's one reason it's going to probably appear stronger. What's the other reason it's going to appear stronger? It's closer, we're traveling through less material, so there's going to be less acoustic impedance and attenuation of the signal going on. Okay? So you just got to kind of keep that in mind. That comes more into play if you're actually trying to like measure the size of flaws deep in materials and that kind of thing. You got to understand that. And we aren't going to go that far. That's more of getting into like a level 2 or even a level 3 application of this versus what most of you would see out in industry would be a level 1, unless you decide to go specifically into NDT and specialize in ultrasonic test. Most of the time you're not going to have to worry about that, but just kind of understand that can take place. To show how that works, we need to know where that near field is. So what we have here is, how do we know where that near field is? Well, near field distance, how far from the transducer face we are, the diameter of the transducer squared times the frequency divided by 4 times the sound velocity. So if I hold up these two probes, I've got in my left hand, the probe for composites, that is a 1-inch diameter. And in my right hand, I have a probe designed mainly for metals. That's what is this one about? I can't remember. 0.37 inch diameter. So of these two, which one is going to have the deeper near field? Which one is going to be able to detect, going to be worse at detecting surface flaws? You see Nick pointing to my left hand. You're right, my left. Yeah, that's the big one. That's this one designed for composite. So we got these big transducers like this. They're much better for composites, but they're not going to find surface flaws. They're more looking for things like delamination deeper in the material. Okay. Versus with metals, something like this smaller one's going to be better for finding cracks that maybe are a little bit closer to the surface. And then we also have to keep in mind how the velocity is going to change, right? Velocity is fixed by the material. We can't do much about that. But typically, velocity is going to be slower in composites than it is in metal. So with a smaller denominator, that near field's going to be bigger as well, right? So it's a lot harder to detect surface flaws in composites than it is in metals, okay? So really, all the probes I've passed around besides this big one are designed for metal. This is the only one we've got that's designed for composite. I've also got up here an angle probe, which we can talk about. This is another one designed for metal. It doesn't mean you can't try them for other stuff. That angle of divergence, that gamma, if you do need to figure that out, here's the equation for that. So it's 1.2 times the sound velocity, divided again, frequency and diameter of the probe. The diameter of the probe and the frequency that you have your transmitter set at. So this may come into play again if you're ever trying to measure flaw size deeper in an object, or you need to know how wide that beam is at a given distance. This will give you that angle. So just to try these real quick, I got a couple examples. So if you want to get out pen and paper or something to write down, I'll write it down on the board here. I'm in a bad spot. But let's figure out what the near field distance is. If we have, and this is all the easiest way to do this in all honesty is to do it in metric. There's a lot less unit conversion, so we'll do it in metric. So velocity of our material, I'm going to do aluminum, is 5,100 meters per second. Okay. The frequency we're going to use is 1 megahertz or 1 million hertz. The diameter of our probe is roughly 0.5 centimeters, but they all need to be in the same unit, so it's 0.005 meters. Half a centimeter is 0.005. What is the depth of our near field? Okay, so the near field in this case comes out to 0.0012 centimeters, okay? So, meters, 0.0012 meters. Oh, I said centimeters, okay? 0.0012 meters. So it comes out to just 0.0012 meters, which is, move that over, it's 0.12 centimeters, which is just over 1 millimeter into our part. Okay, so that top millimeter of our part, we would not be able to reliably find any kind of cracks, discontinuities, or damage. Okay, because of that near field interference that's taking place in that area. Quick reminder, longitudinal versus shear wave propagation. So we talked about that at the beginning. We reviewed it real quick. If you need the visual. The reason I bring that up is because now we're going to look at some of the other ways that we can do this. So we've talked about, on the left here is a pulse echo transducer. That's what everything I've passed around up to this point is, a pulse echo. Or if you put another, if we did put another transducer on the bottom, we could put a little receiving transducer down here, and that would be what's called a through wave, or a through transmission. Okay. In some cases, though, rather than using a longitudinal wave, we can use a shear wave in order to go off to the side. So that's what's shown on the right here, is angle beam testing, which uses a shear wave. And so I've got an angle beam transducer here. I'll pass it around. And if you look inside of this, there's a clear acoustic material, just like our delay line transducer. But the actual crystal, the actual transducer itself, is mounted in there at an angle. And so that's going to send out a pulse at an angle. What's the angle on that? It should say on the side. Is it a 45 degree or 60 degree? See, I'd have to look at it. But what that allows us to do is that shear wave, now you can see if there were, so a couple things you got going on. Just like, I'm sure you've all seen a straw in a glass of water, and where the straw goes into the water, at the surface of the water, it looks like it's bent, right? Because of the refraction. Well, sound has that same refraction when it goes through, and when it goes through an acoustic interface, you're going to get some refraction of the sound. So you can see the angle that the transducer is at is not the same angle necessarily that the sound is going to travel through the part. Okay? And so what that'll do is, now if we have a discontinuity that even is off to the side a little bit, it is going to cause sound to bounce back, and it's going to alter that shear wave that we see. So now we can use that to test off the side. So where this is often used is, imagine if you had, you can see these transducers have to be on a fairly smooth part. Imagine we had like a weld right here. Okay. We can't go directly above a weld because it's not a smooth surface. And so oftentimes angle beam testing like this is used to check a weld. And you can see as you move this to the left, if we move it to the left, the sound would come in and it would hit further down. And if we move it to the right, the sound would come in and hit further up. And so we're able to move it side to side, left to right, and we're able to scan up and down the height of that weld to check for something like proper weld penetration, or look for voids or other stuff like that. So you'll see angle beam testing used in those scenarios.